the first bit was all about especially CSH, which is what causes us most of our headaches in trying to understand what's going on. And now we're going to go very quickly through the other hydrates. And these other hydrates are important, but generally because they are quite well crystalline, they're a little bit simpler to understand, and also they're present in smaller amounts. So aluminate hydrates is basically three families of aluminate hydrate. The first family is what we call these AFT phases. So this means aluminium iron trisalts. And you see the classic one, which is really the only one we seriously need to consider for most purposes, is this material called ettringite. This material called ettringite, it has this structure, it has this composition C3A, 3 calcium sulfates, and then a lot of water. And this forms nice hexagonal needles. You can even get, macroscopic crystals in nature. Comes originally from the town of Ettringen. This is quite well established. We can get carbonates for sulfates. We can also have thalmosite, but we don't really need to be worried about that on the first level. So you can think interchangeably using these two names, AFT and ettringite. And generally, I'm probably going to call it more ettringite later rather than AFT. Second family is this family we call the Afm phases. And the point about these is these are aluminate ferrite mono. Instead of 3 other ions here, they just have 1. The question is that these 1 other ions can be very, very variable. And we do get a lot of different Afm phases. We get a lot of solid solution between these Afm phases. That's to say, we may not have only sulfate ions in the interlayer. We may have hydroxide ions, etc. For the purposes of hydration, the 2 most important ones, or perhaps the 3 most important ones, are this phase we call monosulfate. This is where we have instead of having 3 sulfates, we have 1 sulfate. The hydroxide AFM, which is also called C4AH13, and also the monocarbonate is important because this is how the small amounts of limestone can react. They can react to give carbonate ions, which go in these Afm phases. So because there genuinely is so much variation in this Afm phases, we tend to use loosely the word Afm just to talk about them collectively. Finally, if you cure at high temperatures for long enough, you will form what's called hydrogarnet phases, which are typified by C3AH6. And the exchange that's important here is, sorry, that's wrong, cross that out. It should be exchange between silicon and water. I'll have to correct that. Okay, so where are these aluminate phases coming from? They're coming mainly from the hydration of C3A, and to a minor extent from the hydration of the ferrite phase. If you hydrate aluminate phase on its own with water, you get a very, very violent reaction, a very, very quick formation of big plates of hydrates, and you get stiffening, which is called flash set. And we don't want that to happen in Portland cement, and for that reason, this is why we add sulfates, okay? So this thing here we don't need to worry about because this is not what happens. What does happen is you have C3A which reacts with sulfate. So this is usually written as the reaction of C3A with 3 moles of gypsum to form this compound ettringite. Of course, what really happens, as with all hydration reactions, is that everything goes into solution and forms ions, and then those ions precipitate out of this phase. And for that reason, I mean, it's important to see here that these calcium ions didn't necessarily come from this C3A. These calcium ions could have come from C3S or whatever, and they're forming ettringite. And once all the sulfate ions are used up, you get this second reaction, which is the ettringite that formed already in this first reaction reacts with more C3A to form these monosulfo aluminate phases. So we're going to see what that means in terms of microstructure. So here's some pictures of the reaction of of C3A. These are taken in the wet cell in a transmission electron micrograph, so they're as near as possible to undried samples we can really have. And what you see here, here's your C3A grain, here's your ettringite crystals. We can actually see that close to the surface there's some other kind of crystals. Now, what's important to see here is if you read textbooks, and I mean quite honestly, I would say to people most of the time don't read textbooks because there's more things that are wrong in textbooks than right. Because if you read textbooks, this tells you that the reaction of C3A slows down because you form a shell of ettringite. This is nonsense. You don't form a shell of ettringite. You see, you've got these little ettringite crystals here, and how can this little ettringite crystal be blocking the reaction of that C3A with the water? No way. In fact, what happens is the sulfate ions that absorb on the surface of the C3A and slow the reaction down. But these are how ettringite forms reacting with C3A. So that's what I've just said here. The reaction of C3A is not blocked directly by ettringite, but is controlled by the absorption of sulfate ions. We can find that later on we form this monosulfate phase, and this is where it kind of gets complex because the phases that form will depend on the local conditions. So again, you read in the textbooks, all the ettringite disappears and we form monosulfate. And then you can see this kind of micrograph, and you can see in this micrograph, you can see monosulfate here. These little plates here are monosulfate, and this is ettringite here. Okay, so you've got the same sample, a few microns apart, you've got ettringite here and monosulfate here. So the point is it depends on the local conditions. Here, this is a kind of a shell. This is like the shells of CSH we saw before. And inside the shell, you probably still had some aluminate phase. And because you have that aluminate phase there, that's why you form the monosulfate. Whereas outside, where it was kind of a little bit isolated, these ettringite needles, these can persist essentially indefinitely. So now let's talk a little bit about kinetics. Well, actually, I'm not going to talk much about kinetics for reasons I'll explain. Okay, what happens, what's the basis of mechanism of hydration? The basic mechanism of hydration is that things go into solution and then they reprecipitate. That seems quite a simple thing, but there was an awful lot of debate 100 years ago about whether this occurred or whether it was a solid-state reaction. You still read in a lot of textbooks, people say there are solid-state reactions. There are not solid-state reactions in cement because, not least, the crystal structures of the hydrates are totally different from the crystal structures of the anhydrous. Okay? If you have a kind of a bit of metal and it tarnishes or forms a kind of oxide, that can be a solid-state reaction. But usually you'll find there the crystal structures of that oxide layer is very, very similar crystallographically to the underlying crystal. And therefore it can occur in the solid state. Hydration reactions do not occur in the solid state. They occur through solution. Now, what does that mean and what are these curves here? I hope all of you are familiar with the idea of the fact that if something dissolves, it can continue dissolving to a certain level and then the solution is saturated. So say, for example, you take sugar, you put sugar in your tea. If you put in 1 teaspoon, it dissolves. If you put in 2, it still dissolves. And you put in a bit more, then it doesn't dissolve anymore because the solution is saturated with respect to sugar. Now, the important point about cements is that our phases, C3S, C2S, etc., can dissolve and go into solution. But then we get something different happening because then the ionic species can get together in different combinations and can precipitate new compounds. Okay? So that's what I'm trying to show here on this slide, is that we have a solubility of the cement phases which is much higher than the solubility of the hydrates. And it's this difference in solubility that drives the hydration reaction. It's a thermodynamic process. And when we initially add water, we start from pure water without any ions dissolved in it. As the materials start to dissolve, they dissolve, they dissolve, they cross this line of the solubility of hydrates, they have to go to a little bit of supersaturation to form the first solid, and then this solid precipitates and the solution composition goes back to this level. And by understanding all of this, it's now very easy to take a thermodynamic calculation and predict what kind of phases form. Works very well. Now that's thermodynamics. That's why it happens. Now we look at the time scale, the kinetics, and this is a time scale of the reaction of A-light. A-light, C3S, is the main phase that's present. And this time scale, this is measured in terms of the heat evolved. As the reaction goes on, it gives out heat. So we have a very easy way of tracing the reaction. We put our sample in what's called a calorimeter, and this is a very sensitive information that can measure the amount of heat evolved over time. So what we see is that when we first mix with water, we get a very violent emission of heat. Okay, this only sort of starts plotting here. It actually goes up much higher. That heat of reaction, so the reaction then slows down. It stays at quite a low level, and then it starts up again. I'm sorry, but I haven't got time to discuss all the mechanisms behind these different stages. From a practical point of view, it's very important, because what this fact that it slows down and then speeds up means is that you've got time to make your concrete, transport it to the building site, put it in the form before it starts setting. If you didn't have this slow down before it restarts, then you would never be able to use concrete in a practical sense, because it would just stiffen immediately you added the water. So this slowdown and this low period of reaction here is generally called the induction period. So you'll see this in textbook called the induction period or dormant period. There's an awful lot of controversy of what's behind that. I think we now have progressed a long way in understanding, but I just don't have the time to go into all the details of that. At any rate, from the point of view of this project, we're really interested in what's happening somewhere out here after several months of reaction. So we're going to focus mainly on, after this, we get this, you see, we get this reaction starts up, it accelerates, then it slows down, but it doesn't actually go to zero, and it stays at this level for quite a long time. So that's A-light. And then if we go from A-light to cement, you see that it's really pretty much the same. The scales aren't quite the same down the bottom here. But we've got two extra little reactions here. These little bumps here are due to the aluminate, and we get two reactions. First of all, we get a second formation of yttriite, and then we get formation of Afm phases. And this is another picture which is at variance with what you'll see in most textbooks. And I haven't got time to go into the details of why the textbooks are wrong. You just have to take my word for it, or we'll discuss it later. But what's important to see here is the dominance of this A-light phase, of this C3S phase. Because you can see like 90% or I haven't got the exact figure, but by far and away, most of the reaction is this underlying reaction of the A-light phase, with just this tiny little add-on bit of the aluminate phase. And this is why the C3S reaction is so important. So now let's look through this curve what's happening microstructurally. If we look after about an hour or so, you see this is the surface of my A-light grain. This is a big A-light grain here. This is 1 micron. And on the surface of my A-light grain, I've got a few little rods of yttriite. I showed you before that this yttriite formed very early on. And I've got sort of maybe a little tiny bit of CSH that's also starting to form. I get to this point here, the end of the induction period, about 3 hours. I'm starting to form my CSH, like I showed you before. And through this acceleration point, this CSH is forming more and more. We come to this point, it starts slowing down. We're pretty sure now that most of the reason for this slowdown is space being used up. Okay, so as the CSH from one grain starts to meet up with the CSH from the other grain, there's less space for it to continue forming, and this is why the reaction starts to slow down, but it will still continue. We see this little bump here. I told you was the secondary formation of ettringite, and this is what we can see. We can see these needles of ettringite which form. And then when we have this monosulfate reaction, we start to form these monosulfate plates, as we saw before. Okay, so that's really the essential sequence of microstructure formations. Anybody got any questions there? No? Everything's clear? Yes. I'm glad somebody's asking questions, because all of you seem to be very quiet.
Well, I must admit that I like to read textbooks, and you have said now for many times that textbooks are wrong, or most textbooks are wrong. What is a textbook which is less wrong, and which is maybe readable without being ridiculous?
What I'm writing that I haven't got time to finish, but should be finished in about 6 months.
Okay, may I have your draft before? Okay.
So, I mean, I'm just warning you, because the problem is that, you know, there isn't as yet a good textbook, particularly a good textbook from a material science perspective. You know, we have textbooks that are pretty good from a civil engineering perspective that tells you how quickly the strength is developing and things like that. But from a real material science perspective, there's really very little available, unfortunately. And, I mean, even so, most of the stuff I'm showing you here is comparatively recent. I mean, most of this understanding of microstructural development is work that's been done in the last sort of 20 years or so. So, you know, I mean, 20 years is quite long for you, because that's probably most of your life, but for people like me, it seems quite short. Okay. Now, okay, as with anything in cement, we have a simple level, and then when we look into it in more detail, things get more and more complicated. And one of the things that's more and more complicated is the formation of what is often called Hadley grains or hollow shells. And you can see in these transmission photographs, so the dark stuff is the cement grains, and the bright stuff is where you've got holes, where the electrons go straight through. You can quite clearly see that this first product of CSH is like, it's not quite attached to the underlying grain. We now know that there is actually something in this space. It's just very, very low density. And this kind of feature persists, and you can see, I'll point out to you later on, that a lot of these pores we look at are these little hollow shells. In fact, if I zoom back here a bit, sorry about this. So I zoom back to that micrograph here, which is the one I showed you earlier on. Now, when you start looking at that closely, you can see, for example, here we've got a small grain which seems to have a hole in the middle of it. And when we start looking closer and closer, we can see a lot of these fine pores, like that one here. That was a very small grain that left a hole in the middle of it, and so on and so on. So a lot of these kind of porosity we see in a final cement paste is actually due to these hollow shells. And we don't at all understand, you know, how that really affects things. You might think because those are hollow bits in the middle of grains, they're not connected. How and if water gets into them is another big question, etc. So these hollow shells are very, very important in terms of they're everywhere. What difference they make in terms of transport is an open question. And the presence seems to be very much affected by aluminate. So again, we've got aluminate presence in very small amounts, but even in these very small amounts, it can have a big influence on the arrangement of microstructure. And so this is just summarizing the microstructural developments. This is a diagram I did in 1984, and I think it still stays more or less true today. And the article that's in your folders, which I wrote in, I think, about 89, describes all of these steps in more detail. And I think most of what's written there is still more or less valid today. So that's the kind of, again, a final microstructure. Again, you can see the importance of these hollow shells. Of course, you have to accept that when you're polishing, you might get, some grains might disappear, but you can now start, if you now start looking, you can start to see these hollow shells everywhere. And if you look at a micrograph of quite an old paste like this, you can now start to see that a lot of the grains that are left are actually your B-light crystals. So you remember I told you that B-light had this rounded shape, and this rounded shape you can now spot in a lot of these grains here. So let's come back and now let's look at how all the different phases react. So this is data from the thesis of Vanessa Kokova, where we studied how these different phases reacted in detail. You can see, of course, there's a lot of variation from one cement to another, but we have the same general pattern. We see here, this is the C3S, the A-light phase. You can see by 10 days, this has reacted about 80 or 90%. So it's almost all reacted in the first 10 days. In contrast, in very stark contrast, it seems the B-light hardly starts to react before 10 days. And we actually think that this is a good reason for this, that while A-light is reacting, it actually blocks the dissolution of B-light. Because B-light has such a lower solubility than A-light, the reaction of A-light actually suppresses the reaction of B-light. So this is also why, it's actually best to have A-light in your cement rather than B-light, because the B-light's not reacting till very long times. Here's the Aluminate phase, and you see the Aluminate phase is reacting very, very fast. By a few days, it's almost 100% reacted. And finally, we have the Ferrite phase. It's reacting less fast than the Aluminate phase, but it is reacting significantly, so that by 100 days or so, we have about 80% of it reacting. And this means that in mature paste, so these are actually micrographs of a piece of concrete that had been in a building. It was about 30 years old. And you can see here we've got a nice dense microstructure. You can still identify the cement grains. And we've even looked at cement which is about 100 years old, and you can still identify where the original grains were. You can now see that the grains that are left tend to be B-light grains. You can see these rounded crystals, and they tend to be these very large grains where B-light grains are held together by ferrite phase. I said that the ferrite phase was actually 80 or 90% reacted, and this is another interesting point, because you can still see this ferrite phase, that it's very bright because iron has a much higher atomic number than the other elements. But probably what's happening here is that one of the things that forms from the hydration of the ferrite phase is iron hydroxide, and this iron hydroxide is just taking the place of the original ferrite material. And weird things we have, this is a B-light grain that started to react, and you see it doesn't react evenly, it reacts very unevenly. And this is the kind of, again, complications, the B-light structure, due to the cooling from the clinkering temperature to room temperature, forms these kind of twin structures, and almost certainly we have impurities which segregate in these twins and give it this different degree of reaction. So that's what I said. In old concrete, you can only see B-light. And that's what I also said, that XRD shows that the ferrite reacts, but these images show that it seems to be still there. And that's because the alumina and the lime kind of react out, and they leave behind this iron hydroxide relic. Now, we've seen a lot of this kind of outer product. And you see in all these micrographs here, it's sort of, it's a jumbled up mess. It's kind of very variable. But it's very variable, but it's also a very finely intermixed material. So here's a kind of schematic zoom of one of these areas of this undifferentiated, this outer product. And on this fine level, we have CSH, which is represented by this background here, and within the CSH, we have little tiny crystals of either ettringite or monosulfate intermixed at the submicron scale. And this can be seen quite nicely in the transmission electron microscope, in the scanning electron microscope, which has lower resolution, and particularly when we try to analyze what are product is, when you make an analysis in the scanning electron microscope, as I'll show you this afternoon, you're actually analyzing quite a large volume, a volume of about 1 to 2 microns. So you can't separate these phases on the scale of microanalysis. And this is why we make these kind of plots here. You do many, many microanalyses on your material, and then you plot the points like this. And this, here you can see a lot of scatter, a lot of intermixing. Along this line we have mixtures going to monosulfo or ettringite. We can better distinguish them on this one. Here on this plot, which is sulfur calcium versus alumina calcium, you can see we've got this cluster down here, which is our CSH, and then we've got very small crystals of ettringite mixed with that CSH, which gives us these points going up here. And as we go on to later samples, you see that the ettringite starts to decrease, and the amount of monosulfate intermixed now starts to increase. But we still have this cluster that represents our CSH composition, and we can use that cluster to really get a quite good idea what is the average composition of our CSH. So our average CSH has a calcium to silicon ratio here, and a sulfur to calcium ratio, etc. As we go on in time, we can often see things like this. We often see these packets of, so this is our sort of microstructure, and we've got these little packets where we've got these kind of crystals like this. And we can analyze these crystals, and we can determine these crystals that actually have the composition of ettringite. So early on we saw these long needles. Later we see these large masses. We see they've got these cracks in them. These cracks are again an artifact of drying, because the water content of ettringite is quite high, and as with CSH, as we dry it out, it loses water, it shrinks. So, you know, these cracks are just an artifact of the fact we dried something out. A lot of people are saying, okay, if you see these packets of ettringite like this, this is a sign of degradation. Again, sorry to keep disagreeing with what people write, but it's not a sign of degradation. It's a sign of an old concrete which was, you know, wet to quite a lot of time, because this is just a recrystallization. We start with ettringite finely intermixed in the CSH. Over time, these tiny crystals, they want to reduce their surface area, and they reform as these larger crystals here. So this is a normal process of recrystallization and crystals growing larger, which occurs in a lot of systems. So two points to finish. First of all, what's a very important element affecting the microstructure is temperature. Okay? So you need to be aware that of the effect of temperature on microstructural development. Now, temperature, first of all, has a big effect on kinetics. So this is our heat flow. This is a typical curve at 20 degrees, and we see this maximum is around 10 hours. We go up to 40 and to 55. You see the reaction is very much speeded up, but the reaction has the same basic form. And this speeding up effect can be well described by the classic Arrhenius equation, where there's an activation energy for a reaction, so as you increase the temperature, the reaction goes faster. We should perhaps say that this activation energy is kind of more of an apparent activation energy, because you have several different reactions going on. What is so important is that when you look at various properties, you see something rather strange. So if we look at this development of strength here, you see that at 1 day, for example, the one that's hydrated at 60 degrees has a much higher strength than the one hydrated at 20 degrees. Well, you'd expect that because the reaction's faster. You've got much more reaction. But what you don't expect is what you see over here, which is at quite long times, the material that's hydrated at 60 has a much significantly lower strength than that hydrated at lower temperatures. And when we come to something which is kind of a broad indicator of durability, i.e. water absorption. So what this is, you dry your sample out, you then put it in contact with water and look at the speed with which water is sucked up into the sample. You see that the rate of water absorption, even at the young ages, is very much higher in the material cured at high temperatures compared to the material cured at low temperatures. And that's not what you want. You want a slow rate of water absorption because in terms of degradation, you have something being wetted on the outside and you don't want it to be absorbing into the material fast. Now, what's the reason for these very different performances for something cured at high temperature due to low temperature? And to understand that, we need to better get an idea of these properties, not as a degree, in terms of time, but in terms of the degree of hydration. So here, we measure the degree of hydration, we measure the strength. Of course, there's a bit of an error on all of these points, but very, very clearly, you can see the strength for the materials cured at high temperature is much lower at the same degree of hydration than those cured at low temperatures. And then when we go to investigate this further, we can actually see that the temperature has had a quite dramatic effect on the calcium silicate hydrate phase. So this one was cured at 20, this one was cured at 60. You can see here that the CSH here is much darker than the CSH here. And the fact it's much darker, this indicates it's less dense. So the brighter color indicates a higher density. And you can measure this systematically. What's the gray level? This is what's shown here. So you see 20, 40, 60. The gray level, proportional to the density of the CSH, increases. So what does that mean? This means that for a given amount of hydration, you formed your CSH in a more compact, denser fashion, so it occupies less space. And the fact it occupies less space then means you have more pores. So you should be able to see, even visually, we've got much more of these black pores in this bottom one than this top one. And the fact we've got much more of these pores is then why we have the lower strength and the higher rate of water absorption. So again, temperature is an important factor. We know it's affecting directly the CSH, and this goes back to what I was saying in the first half. We've got this incredible complexity of our CSH. We saw we had these nanocrystalline regions, and we saw we had water in all the different states, and now we see that all of those are changing when we change the temperature. So again, a question where we know some of the answers, but not all of the answers. And this just shows concrete that was cured at 2 different temperatures, and you can really see here in one and the same sample this dramatic contrast between the 2 different types of CSH. This one here was formed at a very high temperature, in this case 90 degrees, and then as it went on reacting longer and longer, we had this product that was formed afterwards, which is less dense. And it also shows that once something's formed, it doesn't go back. It stays like it was when it formed. Because this cement paste, this was cured for over a year at room temperature, and it didn't change this CSH that had originally formed at the high temperature. So 5 minutes to go. We're just going to say a few words about volume changes, because this is important in terms of forming pores. Just before I go on to that, anybody want to ask any questions about temperature? Yes?
I wonder if we can use the increasing of temperature to have an idea of the mechanism at later ages, just in terms to have a short time of experiment.
Yeah, that's a good point. That you're talking about exactly for your project, but that's a good point. I'm not going to answer it generally because I think it would be too confusing to everybody else, but we should discuss that. Okay. Okay, so volume changes. So I told you right at the beginning the most important thing is the volume changes. And here we're writing down in more detail the volume changes for our C3S. Okay, so this is a reaction written in terms of volume. It says 1 volume of C3S reacts with 1.318, I mean, you know, we don't really know it to 4 decimal places, but 1.3 volumes of water to form 1.5 volumes of CSH and 0.6 of calcium hydroxide. So you see here that we started with 1 solid volume here, and we end up with 2.17 solid volumes here. We roughly double it. Okay, and we haven't just got C3S. If we write down the reactions for the other phases, they're all slightly different. Overall, it comes out about double. But what's more important is that you see the total here is slightly larger than the total here. That's what you have to see in this slide here. That overall, on hydration, you slightly decrease the total volume. And the decrease is what we call chemical shrinkage. And in this example of C3S, it's about 7%. And depending on the assumptions you make and what the composition of the Portland cement, it will generally be about 5–10%. Now, this is a little bit annoying because, in fact, it means that you can never have 0 porosity in a cement paste. Okay, so I showed you the example right at the beginning of a water-cement ratio about 0.3, where we had a solid volume at the beginning of about 50%. If we could go to complete hydration with none of this chemical shrinkage, we could actually remove all the porosity, but we can't because we have this chemical shrinkage. And this is really, really important, this chemical shrinkage, and it occurs in all hydration reactions. Again, you'll see in textbooks that people talk about expansive reactions. So this is a classic expansive reaction, the reaction of free lime with water to produce calcium hydroxide. In the right situation, this can be used as a silent explosive. It can even crack rocks apart. But the overall volume change is to decrease. Again, Ettringite. The Ettringite reaction is a reaction that's often associated with expansion, but if you write down the equation, you work out the volumes, it's an overall volume decrease. And the reason for this overall volume decrease is quite simple. When you have water moving around in the liquid, each water molecule occupies quite a large amount of space. When you pin that water molecule down in a crystal, on average it occupies less space. And that's why you have this chemical shrinkage. And it's quite nice because it provides us with a very simple and cheap way of following the hydration process. So this technique has been available for a long, long time. Meta actually worked on this technique for her PhD. And the simple idea is that you have your paste in here, you fill it up, you have a little container here, you completely fill this with water, and then you have a capillary tube that's going up out of the sample, and as the paste is reacting here, the overall volume is going down, and to replace that volume, it sucks in water, and you follow that water being sucked in by this drop of oil on the top. Now, when Meta did her PhD, she used to have to go along and write down the position of that oil drop at the top of the pipette, which can be very tedious. Now we have this nice little webcam which we can buy for a few tens of euros, and we can focus on these oil drops, and we can do it all automatically by image analysis. So that's all very nice, and it means you can have a setup to continuously follow hydration for effectively the price of a water bath. And this then shows two repetition of volumes. I think Meta's going to talk more about this on Wednesday. So this is just an introduction to the idea here. This looks at then the volume changes, the chemical shrinkage, according to 2 different water-cement ratios. And the 2 different water-cement ratios, you see in this one here where you have a water-cement ratio of 0.5. You have plenty of water. This is water here, and this is just done for C3S. So this is C3S hydrating. So this is at the start, you have about 40%, as we calculated right at the beginning. And then as that C3S reacts, the volume of C3S is replaced by CSH and by calcium hydroxide. And when all the C3S has reacted, then you see you still have some water left over. And because of your chemical shrinkage, you still have some voids. In the second example here, you're at a water-cement ratio of 0.3. And the important thing here is that at a water-cement ratio of 0.3, you don't actually have enough water to completely react all your cement. So this is another reason why we can never get rid of all the porosity. The other message in this slide is to see that if we don't have enough water to react all the cement, it doesn't matter. This material here is still going to be stronger at the end than this one here, because strength and nearly all other properties depend on the total amount of water plus voids, total amount of pores that left over. And we see in this case we've got a much smaller amount of porosity here than we have in this example here. So, sorry, I thought that was the last one. Interfacial transition zone. I promise this is not more than 2 minutes, because this is just everything we've said today is talking about cement paste. And in reality, we've got concrete. Concrete, we have aggregates. And we know that the microstructure around aggregate is not the same as in the bulk cement paste. And the reason it's not the same is for this very simple reason. Here's a cement paste. If we put an aggregate there, the grains can't be cut by the aggregate. You know, they're physically pushed out of the way. And this is what's called a wall effect, where we tend to find fine grains in this region here and larger grains further out. And the consequence of this is that the porosity, the free space here, is higher right against the wall than out here. And we can measure these effects. We can take an image and we can make these little bands, and we can measure the amount of all the different materials in these different bands. And we can look, for example, at the distribution of the cement grains, and this is just the quantification of what I showed you in these images, that as we approach the aggregate surface, we get less and less volume of cement grains. So the measurements are the blue, the red, and the grey, and the green is what we can back calculate from the different volume relationships. Because we've got this higher, we've got less anhydrous grains here, we've got more space, and the fact we've got more space means that actually this favors the precipitation of calcium hydroxide in this zone. And this is quite good because we had more space to start with, more calcium hydroxide has formed in this space, so it tends to cancel out to a large effect this extra porosity. But in all these graphs, what I want you to see is this effect it's quite small. We're talking about differences on the scale of 10 or 20 microns. But in a typical concrete, if you add up all the layers of 10 and 20 microns around all the aggregates, this can make up quite a substantial part of your concrete. We finally come to this one here, which is the porosity. And here you can see quite clearly in this 10, 20 micron zone, we have considerably higher porosity right at the aggregate than in the bulk cement paste. And this was, of course, very important in terms of transport, because in terms of transport, it means that it's much easier for things to penetrate into a concrete around the aggregates where we have this more porous area than it is through the bulk. So I think that really is the end, and we're not too much over time. So thank you for staying with it. Anybody got any questions before we break for lunch?